y se instaló. Se instaló, está bien, aquí están. Ahí se instaló. Está bien. El complot se instaló, bien. El radio, versión, gracias por la información. Limpiamos esto, creo que está limpio.
Hello. So some people are having issue with, some people are getting errors with this line here, right? What you need to do is, if you have any R session open, just close them and leave workflow 1. So I'm going to close my regression model 1. I close it, right? So now I'm left with workflow 1. Save workflow 1. Click on the save button there. And then close it. So close any R session that you've opened with the exception of workflow 1. Then you save, click on the save button. When you save it, now we are going to close everything. So you click on the close button to close this one, but it will ask you save workspace image. Click on the save. We are going to open it again. Go to your script. Then open workflow 1. Then if you have already installed your packages, load them and then run this line. It will not give you an error. It's a collection of functions which we are going to use. It doesn't really know the path or the area that that script is located. Are you okay? Yeah. Is it now working for everyone? Working? Hello? I heard it's time for our coffee break, so we can go for coffee. When we come, we'll continue with our model. Hello. Can we start now? So I hope everybody has read in their libraries, right? And you have also changed your drive path. This is my drive path, so don't copy the same thing. Make sure you use your own drive path. And we have our input path and then our model path. We are actually using, in the first workflow, it's based on simulated data. So the input path is actually not, necessary, but let it be there. So run my own from the library, from the beginning. Yeah. And also, please make this correction. So your model path, it should be day 3. So there should be a space. Then you have your scripts. Then you bring that slash sign. Make that correction. It was a mistake in the previous script. So model path, make sure you write day 3. Yeah, day 3. Okay. So please don't change anything here. You changed it before. Mine is different.
Donde dice en el drive path, en el drive path habíamos cambiado solamente no sé cómo se dice, el underscore, la rayita en la mitad y day 3, lo teníamos arriba, ¿ok? Déjenlo así, él lo está cambiando para que le haga acceso a su directorio, ¿ok? Como lo tiene él en su directorio.
All right, so I'm reading from a different directory. All right. So the next thing we will do is some kind of visualization. So we will plot a graph called directed acyclic graph, right? It's just to see what's your parameters, your data set. It's just a graph. It means nothing. This is just some visualization. So run line 19. Have you all run line 19? Right. So if you run line 19, we are just plotting the parameters that we need to estimate. So are we okay? If you are having error, it means the ggdark package is not installed. Okay. This is the plot you've actually run it. So install this package. Okay, can we move on? Are we all seeing the graph? Right. So this is just a graph showing our regression parameters. So if you remember in the introductory, I told you alpha, which is our intercept. Then we have our beta, right? And then we have our sigma here. So those are the blue circles are the parameters that we will be estimating, right? So usually when you add your alpha and your beta, you get what is also called a mu, right? So this is just a graph. It doesn't mean anything. It's no analysis, just some visualizations that you can use when you are doing some work so that, you can use them in your presentation whatsoever. So we are moving on. We are going to use RStan, right? But before we use RStan does a simulation. And so it needs your machines, they have cores, what is called cores. So we will be using the cores on your machine to do the simulation so that it becomes very fast, right? So this line 38, options mc.cores, is to detect the number of cores on each and everyone's machine. So when we are doing the simulation, the software will split your data set to different chains and they will run so that the results can be done in a very quick manner. So this results here, and this line here is what we are doing. So run that particular line 38. And line 39 is to speed up the process of computation. So run line 39. Right. Are we okay? Then now we are going to simulate some data sets to use it to fit our first Bayesian model. So just like yesterday, when we were simulating the data set, we set the seed so that everybody will have the same number. If you clean this one, if you clean the seed, you will get different results from what we are going to have. But in order for everybody to have the same number, we set the seed. So we are setting a seed. And then we are simulating our dependent variable from a normal distribution. The n represent the number of observations we want. And we are saying that our normal distribution, the simulated data, should have a mean of 5 and a standard deviation of 50. So just run that line. We are just simulating some data. So if you want to see the data set that you've simulated, you click on the data in the environment. So this is the data sets, the observations that we have simulated, right? When you finish, you can close it because we don't need it. Okay. Are we on track? Any problem? Okay. The next thing we want to do is to look at the histogram or distribution of our data set. So this whole script here plots the distribution of our data set. So when we plot the distribution of our data set, it says that the mean of the simulated data is 7.53, and the standard deviation, which shows the variability within our data set, is 49.59. So these are just normal graphs. They are just some descriptive statistics that you can use in your work. So are we okay? The next thing is we are going to plot another parameter. So in this model, we are only estimating an intercept. because we don't have any covariates in our model. So there are no independent variables in our model. It's only the intercepts that we are estimating in this regression model, right? So we plot so we plot our graph. So the sigma is always part of this is the error. It's always part of any regression that you do, right? The errors. And we are estimating our intercept here. We are calling it a mean. So the regression analysis that we are coming to do has two parameters that we don't know that we need to estimate. Two parameters. One being our mu here, and then the sigma. And to estimate mu and sigma, we need to give them priors. So this is where the priors comes in, right? To estimate mu and sigma, we need to give them priors. And the priors is defining our level of knowledge or previous knowledge regarding the estimate for mu or sigma. So we are now gradually applying the Bayesian concepts, right? Okay. Close it. Okay, open the PowerPoint slide that we were. Come down. Yeah, come down. Down, down. Down. Okay. This one. Okay. So we have established that we need priors for the parameters that we are going to estimate, which is mu and then sigma, right? So how then do we define priors for the parameters? There are several ways you can go about this. If you have done previous experiments or you have a strong knowledge with respect to the distribution of a particular parameter, you can incorporate that knowledge into that parameter, and that is called an informative prior. So informative prior, if you have a strong knowledge about something, you know that this particular parameter has this distribution, you incorporate it in estimating the parameter, and that is called an informative prior. So an informative prior will have a mean value, and usually it will have a smaller standard deviation. So when the standard deviation is very small and it has a mean value, then it is a form of an informative prior. Sometimes too, if you don't know anything regard to the distribution of the parameter, right? Like my colleague was asking, have you heard of WorldPop? And he said, no. So we have no idea about that particular parameter. We usually use a non-informative prior or even a weakly informative prior. And an example of a non-informative prior is that the standard deviation is very wide. So here we are using a uniform distribution, and we are saying that our prior, the minimum value is 0 and the maximum is 1,000, sorry. So what this means is that we are going to estimate values between 0 and 1,000. And you can see that it's a very long range, right? We are not constraining the model. simply because we have no idea the range of values or prior knowledge regarding that parameter of interest. So in Bayesian, we have informative prior, weakly informative prior, and non-informative or diffuse prior, right? So that's just by the way. Let's move on. Go back to the script. Okay, so in our modeling, we need to estimate mu and sigma. We have no idea the distribution of mu, and we have no idea the distribution of sigma. So we are going to use a non-informative prior, a uniform distribution, which has a large interval. So we are saying our mu will have a mean of 0 and a standard deviation of 100. And that is what we are doing here. Here, we are just defining the priors and plotting them on the data set. So the prior that we are using for mu is a 0 mean and a standard deviation of 100. You can even increase this one to 1,000. And that becomes a non-informative prior because we have no knowledge about it. So we run that line 74. And let's plot it on our data. Okay. So this is the histogram of our data set, right? And we have a density plot of our priors over our data set. So in the calculation, we are just going to multiply, in basic terms, we are multiplying our prior, the probability of our priors with the probability of our data set in basic term, and that is what we are doing. We are also assigning prior to our sigma, and we are saying our sigma should have a minimum value. This is a uniform distribution. We'll have a minimum value of 0 and a maximum value of 200. So we will do the same thing and plot it over our data set. And this is how our prior for sigma looks like when we plot it over our data sets. All right. Are we okay? So we've defined prior. So this is not the computation. We've not done the regression. This is just trying to visualize the distribution of the priors that you are going to incorporate in estimating your parameters. Are you okay? Everything working all right? Okay. So then we are about to fit a model using Stan. And in Stan, we need to define our data. We need to use a list to define our data sets, right? And a list is partitioning our data based on different elements. So it can be characters, it can be vectors, it can be matrices. And that is what we are doing here. We are creating a list of our data sets here, right? So run this particular line. Then before we run the model, we have to still define our parameters of interest. So our parameters of interest is mu and sigma, right? Now, are we all okay? Okay. Go back to the slide. Yeah. Come down. Yep. Yep. Sure. Okay. So the RStan package I asked you to install, in RStan, we actually write the formula of our model. You have to code it directly, right? And RStan is an interface. It interfaces with different programming language. You can use it with Python. You can use it with R. And RStan consists of three main blocks, code blocks. The first one is the data block that describes the data that you are going to use in your model. The second one is the parameters. So the parameters that you are interested in here, the parameter that we are interested in is mu and sigma. You have to code it, and then you come and write your actual model. You write the likelihood of the data set. So RStan is a bit complicated. You need some kind of maybe advanced knowledge to be able to write the code. But here I have written all the codes for you. So you just implement them, but just so you have some background knowledge with it. So close this one. Let us all open our day 3 folder, and let me show you the code that we are about to implement. So day 3, and you go to your scripts. Open your day 3 folder, open scripts. Have you all opened it? Scroll down. Scroll down and open simu_model.stan. So this is the script we are about to implement to run our regression. simu_model.stan. Right. So have you all opened it? Change the properties. Change the properties. Have you all opened Simon _ model? So when you open it, that is how it will look like. See. Are we okay to go? So I have already written the stance syntax. So here is our data block, like I was saying. So I've defined the data that we are going to use here. Then here is our parameter block. I define the parameters we are going to monitor, which is mu and sigma. Down. And then I write our model. So our model is saying that we have a given outcome, which we call y, and we are saying that it's normally distributed, which is a linear model with parameters mu and sigma. And then we assign our priors to the parameters we need to monitor in the model, right? So you don't necessarily need to learn if you want to become more advanced and technical and learn, you can go ahead and learn the code by I've written all the codes for you. This is just an explanation of what we are doing so that you really understand what we are doing. So we are going to run our first model. So you can close the Simon model. Here is we fitting our linear regression. And there are a number of parameters that we need to be aware of. The first one is our data, which we define up there as a list. Then we need to define the number of iterations. So because we are doing a simulation study, we need to define the number of times we run the model. And here I've selected 750. You can decide to write 10,000 over here at the iteration, and your machine will keep running, sampling 10,000 times, right? So you just have to wait for it to run 10,000 times. But I decided to use 750 so that we become very fast. Then in Stan, we also have chains, right? What the chains are doing is that they are sampling from your posterior, right? And they all need to converge at a particular value, which is the mean value. So for example, assuming an incident has occurred, right? And we have 4 people who they don't know each other, but they were somehow at the location of the incident. Maybe there is a crime scene. We have 4 different people. They don't know each other, but they were at the location, or they know something about the crime. And then they go to the police, and each of these 4 people is telling the same story. It's telling the same story. That is what our chains are doing. We have 4 main chains, and they are all simulating, and they will all converge at the same value, right? So in Stan, we use a default of 4 chains in order to be sure of the accuracy of our model. Good, right? So I'm trying to explain some of these basic things to you so that when we're actually doing the population modeling, which is the next one, we will just be running through because we already know what I'm talking about. Then we have what is called a warm-up. So it's like an athlete coming to run. When you are coming to run, like jog or something, you do a warm-up to stretch your muscles, right? You just don't wake up and start running. You may have a muscle cramp. So the athlete will start warming up small to heat up his body. And that is what we are doing. The model is kind of warming up a bit, doing 250 iteration before it takes off. So the warm-up iterations are discarded because they are kind of stochastic, random process. It doesn't know what it's doing. So we don't usually use the warm-up iterations. Okay. And then because we are doing a simulation study, we still need to set what is called a seed so that we will all get the same answer. If you don't set this seed, Stan has a default seed, I don't really remember, but this seed is to ensure that all of us here, if we run the model, we will get the same answer. And we can run the model 10,000 times, and we are going to get the same answer. So we are about to run our first Stan model. We run fit. So run line 105. This pop-up window will show, click on allow access. So Andy, can you click here? Yeah. So our model is starting, it's warming up. This button here, you can use it to refresh to see what is happening. So click on the refresh. So it has started sampling. We have the first chain, which has sampled. We have the second chain also doing the same thing. The third one will sample, and the fourth one will sample. Okay.
The model in the folder was slightly different to the one you showed in the CMO.
Yes. Anybody need any help? So our model is running.
Tengo problemas que me dio aquí.
Day 3.
Do you have any more issues? Oh, we've not gotten here. Wait, yes, yeah. Please, are you okay? Are you okay? Natalia, excuse me. Can you tell him he doesn't have stand installed, so he has to, we can install it now. He has to join other people and just watch. Okay, so tell him. Stand is not installed on your machine. Okay, can we move on? Right. So now our model has successfully run. We need to check whether our model has converged. So, I told you we have 4 chains and they are all running at the same time. So they have to come to an agreement, and that is what is called convergence. So we will run line 114. Can you zoom in? Okay. So if your model converges, it means the 4 chains that we are running, they will be mixing up with each other, right? And you can see that they are all converging at a particular value, which is the mean. So when your chains are mixing up, then it means the model is doing well. Sometimes when you run and your model doesn't converge, you will see one of the chains being thrown off, going somewhere. You won't see that mixing, right? So now it means our model is stable. It has done what it needs to do. So we have estimated our mu, and then it has also converged for the sigma, right? So this is one of the plots you need to check anytime you do a Bayesian regression using STAN. So because it's based on simulation, we need to ensure that our model has indeed converged. Then we need to look at the estimate from our model. So we run our model and we look at the estimate using what is called the cable extra package. It's just a nice plot to show you the model estimate. So you can see we were estimating mu, and it says the mean value is 7.539. We were looking at the parameter sigma, and it's saying that the parameter sigma, the mean value is 49.64, right? So these are, you can call these are the posterior values which have been summarized. You can call them, like if you are looking at frequency statistics, these are the coefficients or the estimates, right? Are we okay? Are we all seeing that? So the rest of the script is just plot. So you see our model estimated the mu value to be 7.54 and the standard deviation of sigma to be 49.64. So we just want to see if we will get the same value with respect to the original data set that we used. So run line 122 and then line 123. Then we plot the two values using the scripts, line 126. So we are plotting our mean. Okay. So our model estimated that the mean value from our regression is 7.53. And the observed value from our data set was 5. So you can see it's not that far off. So the differences that we are getting between the true and the estimated has to do with the priors we used. So sometimes the prior that you use can influence the results of your model, right? But you can see they are pretty much close, having 5, a mean of 5, an estimated value of 7.54. We will then plot our standard deviation, which is the sigma. So we run line 139. So in our data set, it said that the standard deviation of the data that we used was around 50. And our model is estimating a standard deviation of 49.54, which is almost like 50, right? When you run it off to the nearest decimal place, right? So close it. So this is just to plot our mu and our sigma. And now we have done a regression in Stan. Are we okay? Any questions? Okay. Should we proceed? Should we proceed? So if you are having difficulty understanding what we are doing, I mean, it's normal. You are not an outlier, it's just normal. We all struggled when we were learning Bayesian. The more you learn, the more you get used to it. So just take this as the first step. You have learned something new. And so you can carry it on from there and read more on Bayesian statistics to understand what we are really doing. See? So now we are switching gear. We are going to do actual population modeling. So open your workflow 2. Go to day 3, and in your scripts, open workflow 2. Right. You can decide to close workflow 1, but make sure and open my workflow 1 again first. Copy my path. Copy all this, please, and paste it in my workflow too. Yeah. Clean this one. Clean all of them and paste mine. Yeah. Sure. Yeah. So open workflow 2, right? And then make sure you copy your path. If it's not the same, make sure you copy your path from workflow 1 and paste it in workflow 2 if the paths are not the same. But if they are the same, just leave it like that. Yeah, thanks for reminding me. So, Andy, open workflow 1. I need to explain the down to explain the uncertainty to them. The last, yeah. Okay. This one, run this one. Oh. Oh, a bit up, which is a cable extra. Up, 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 up. Yeah, run this one, run this one. And then open this big, let me use it to zoom in. Okay. Can you shift this down? Hello? Yeah, a last thing that I want to also let you know before we leave. So in Bayesian, we have what is called credible interval, which measures the level of uncertainty with regards to any parameter that we estimate, right? So here, we are dealing with the 95%. You find statistician making reference to 95% credible interval, confidence interval. And this is our confidence interval for mu. So the minimum value for mu is 4.60 and the maximum value is 10.445. So it's giving us an uncertainty with regards to the mu parameter that we estimate. And that is it's called the credible interval. So anytime you do a Bayesian analysis, you will get that level of uncertainty, which you can use to gauge. Assuming you are doing a population modeling, you want to find out the uncertainty, what is the minimum population we can get in this area, or what is the maximum number of people we can get in this area. And Bayesian does that for us. So just so you are aware of it, right? So we are now moving to workflow 2 to do actual population modeling. And this time around, we are going to zoom in because I've taken my time to explain what the chains are, what the iterations are, what we are doing, right? So open your workflow 2, click on this button here, this brush here. We are clearing the workspace. Okay, you see everything is deleted. Is there a way of shifting this? Yeah. So we've cleared our workspace. We are now doing population modeling. So go ahead and load the same package. I think they are already loaded from workflow 1. So yeah. Read in your drive path. Then set up your stand. Okay. PowerPoint slide. I'm down. Yeah. Yeah, this one. Okay, so this is just to give you a brief background of the data set that you are going to use. So the data set you are using comes from Nigeria. We did population modeling for them. And so we are using the same data set, right? And it was a micro census where we conducted a household survey between 2016 and 2017. And the number of enumeration areas or clusters were 1141, which were clustered in 15. So we did a study in 15 of the, Nigeria has 37 states. So we did a survey in 15 of the 37 states. And these are the clusters that we collected data from, right? In terms of, so they surveyed household numbers in each cluster, right? Like normal survey, we counting the number of people in each household. So that is the data. So this is just a brief background respect to the data set we are going to use. All right. Okay. So yeah, we can close it. So we read in our data. And the black list. Yeah. This is like series.
Sorry, just can I make one small suggestion, if you don't mind? Please do not advance in running of your script, because sometimes, it's been written by humans, so there might be some error, while my colleague will basically sometimes investigate something and then it will tell you. So don't advance. Please just be patient and let him to let you know which line should be run, just to make sure that we are all on the same page. Thank you very much.
Hello. So have we all loaded our data? So we are going to visualize. Click on line 30 to see our data set. So this is how our data look like. We have cluster ID, and the cluster ID are the enumeration areas that we counted the people, right? And then we have, if you pick a particular enumeration area, how many people were counted in those locations, and that is the population. And then we have the size of the particular enumeration area, which is the area. Then yesterday, my colleague talked about the settlement type data that we use. So each cluster is given a particular category depending on the settlement type, whether it's rural cluster, it's urban, it's a village, it's a town, right? So these are the numbers here. And the region, so region can be something like a province. So the region is like the province that cluster belongs to. And then we have the state. So Nigeria has different administrative units. You have the country, you have the state, you go to the regions, they have local government area, right? So different hierarchy in terms of administration. Shift it here. And our X1, X2, X3, X4, X5, X6 are our covariates that we extract from the raster data, right? So if you remember yesterday, my colleague was showing you the covariates that we can use for the prediction, right? We are going to come to the covariate. I'll explain what X1 means, which covariate is represented by X1, which one is represented by X2, right? But for now, you have seen the structure of our data sets. We know the number of people in a given cluster, and our survey didn't cover the entire cluster. The purpose of the bottom-up modeling is to make prediction across areas where we didn't collect information or population numbers. That is the whole idea about how we do our population prediction. So we collected some samples and we are going to fit a regression and then use the fitted model to make a prediction of human population, right? So we are moving on. So in modeling or predicting population, what we actually model is population density. And then when we have modeled population density, we multiply it by the area or the number of buildings within a given location. So yesterday, we established that population density, so let me make it pop density, is equal to the population divided by the area, right? So if you want to find population density, we know the population, we divide it by the area. So in our model, after we found the population density, we come and multiply the population density by the area to get the population. So it's actually a reverse of the population density formula, right? So that is all what our model is doing. We fit a regression model to find population density, then we multiply it by the area and we get our population. So it's like doing the inverse of this particular formula. Are we okay? So it's simple. If you know this, you can do bottom-up population modeling, right? So here we are just estimating the observed population density, right? We just calculate, we create a new variable called pop density, and then we are saying pop density is population divided by the area. That is what line 33 is doing. So now we check the names of the columns in our data set. So these are the variables in our data set. Are we following? So we are doing step by step, right? And then we will do some visualization. These are just visualizations, so we will walk through quickly. We want to see the first 10 rows in our data set. So we run line 40, and then we get this. If you want to see the structure of your data set, you run line 47. Then we now want to plot our population numbers to see how they are distributed. Any question? I hope your script is running. You are following. So we are running line by line. So now we want to check the distribution of our population. So we do a histogram plot using the ggplot package. So this is the distribution of our population. Now, okay. Now, one of the things we will do is that we know population is a discrete variable. It's a count, right? So anytime you have a count variable, we model it using a Poisson regression. And a Poisson regression has only one parameter called lambda. In a Poisson, the mean is equal to the variance, right? So it just only has one parameter called lambda. So we are building our model incrementally. First, we are going to look at whether if we use a Poisson regression to model our population, will it give us a good result, right? So the first model that we are fitting is to estimate lambda, which is the mean of the predicted population using a Poisson regression. So we just do a direct acyclic graph to plot our parameter estimates. And then, like I said, this is how we represent lambda. Poisson regression has only one parameter, lambda. And because we need to find, so the lambda is the mean estimate, right? Because we have one parameter, we have to assign prior to this lambda regarding the distribution of the lambda parameter. So here, I'm saying that I don't know what the value of lambda is. So I'm assigning it a non-informative prior using a uniform distribution. So I'm saying that lambda can lie between 1 to 3,000, which means that the estimated population for a cluster can start from one person in a cluster all the way to 3,000, which is a very long range because I don't know what lambda is. I don't have any idea of the prior distribution of lambda. So to plot the prior, we need to plot the prior to see how our prior, the shape of our prior, and you run it using line 89, sorry. Right? So when we plot our prior, there's an equal probability of the numbers 1 to 3,000 occurring. It's very flat. You can do some predictive checks to see the effect of the priors that you use in your model, right? So what line 92 is doing is to see if you use a prior for lambda with a uniform distribution, which has a minimum value of 1 to 3,000, we simulate some data set and then see how things will look respect to the priors that we are using. So it's kind of some basic sensitivity analysis to see the effect of a prior on our posterior. So here I just do a simple plot. So this is how my simulated prior looks like, right? I can plot it on top of the data set using line 105. Okay, so when I plot my prior on the population, this is how it looks like. This is not the actual work, just some basic visualization for you to see the prior that we are looking at, how it is distributed. So the next thing is to actually fit our model. And we know that lambda Poisson regression has only one parameter. But in our model, we are also estimating the predicted population for a given cluster, which we called population hat here. Right? So our population hat is that we are predicting, after we fitted the model, we are predicting population for those clusters that we observe population for. So just like we did in our first stand model, we have the stand code model 1, which I've written here, which specifies our data. It specifies our parameter of interest, and then it specifies the model block, just like I showed you in the first workflow. And this time around, we are running 2,000 chains, 2,000 iteration, 4 chains, and we are saying the warm-up period should be 1,000 and so forth. So it's just basically the same thing like the first one. So because we are running 2,000 chains, it will take a while for your model to run, depending on how efficient or computationally faster your machine is. Is our model running? Okay. It will take a while for it to run. So my machine has finally done the simulation, right? So you can refresh to see the chains, how they are running. Come down. Come down. Okay. Run this one, let me see. It didn't show me an error. Run this one, yeah. Okay, so when we run our model, there is also another way of checking whether our model has converged using this particular line 139. So when you run line 139, you will see the NEF, you will see R hat, you will see the number of iterations that ended with divergences. We are going to look at divergences as we go through the model, as well as other parameters. But our model didn't give us any error. So it means our model is doing very well. We plot our trace plot of lambda, since lambda is the only parameter we are estimating. Okay, yeah. Line 142. So we see that our chains are also mixing very well, right? So our model is doing okay. Now, we want to get the mean of our initial population, the observed population, and then we will get the predicted population and see the mean of the predicted population, whether it's similar to the mean of the observed or it's very different. So line 145 to 152 is doing that. So just run from line 145 to line 151. So the mean or the average of the observed population in our data set was around 444.96 people, almost 445 people. So the average population in a given enumeration area from the observed population was 445 people. And our model is predicting very close to that figure, right? We can actually see it when we run the line 155. Sasha, drag this down here. No, this down. This one, this one, this one, this one. Okay. And click on the estimated. Yeah. Okay. So our mean population is almost closer to the observed value that we have from the population estimates, right? So lambda is predicting the estimated or the mean expected population, mean expected population for a given cluster, which is also very close. And we still see the credible interval, right? The credible interval shows the uncertainty with respect to the model that we've currently run. So our model is predicting that on average, the minimum number of people that you get in a cluster is 443.7, And then the maximum number of people you can get is 446. So it shows you the level of uncertainty with respect to the model that we have done. And that is the 95% credible interval. And that's the good thing about Bayesian. You know the minimum and the maximum to give you some level of uncertainty. Now, you can see that you are seeing population hats here. Population hat 1, population hat 2, population hat 3. What we have estimated is that we are estimating for all the clusters in the country, the number of people that the model was predicting, right? So if you take cluster 1, the model was predicting that cluster 1 or enumeration area 1 will have this number of people, 445. So this goes all the way to, I think we have 100 and over 1,000 clusters. So it will predict values for all the clusters that we used in the model. You can close it. Close it, yeah. Okay, so now we are just going to calculate some metrics to see how our model was doing. And this is an in-sample cross-validation, right? Yesterday, if you do remember, we did an in-sample cross-validation using our training data, and then an out-of-sample cross-validation using our test data. But we haven't gotten to doing that. We are only doing in-sample cross-validation. At the later part of our model, we will do the train and test sets. But what you have right now will be an in-sample cross-validation to see how our model is performing, right? So just run line 159. Just continue to run. So this is run. It's okay. Open this chat. Okay, so this is also an example of a scatter plot between our observed population, the population that we actually counted, and the predicted population. And the dots you see are the predicted population for a given cluster, right? We have more clusters, right? The predicted population. And the lines that you are seeing is the width or the uncertainty respect to the predictions that we've made, right? So you can pretty much see if you take this particular enumeration area, for example, the predicted population goes all the way down here. I think maybe, let's say 420, all the way to maybe, let's say 480. But the mean population, the mean estimate is this particular value, which is around 448, right? So you can plot the uncertainty respect to all the clusters that we have predicted population for. And that is an example of a scatter plot. You can also close this one. You can also do a histogram to see how your predicted population compares with the observed population. So here we are doing a histogram. And when we do a histogram comparison of the predicted and observed, the red, or is it pink, shows the predicted population, you can see that our predicted population is very constrained, somewhere around, this is 500. So this would be maybe 448 around the mean predicted population. But we see a large variability respect to our observed population. So these are graphs that you can use to check respect to how your model is doing. You can also, the next thing is a density plot, which is similar to the histogram. And this is our density plot. It's not looking that much. It looks the same. It has the same pattern like the histogram. Okay, then it's time to calculate some metrics to evaluate our model. And we calculate these metrics based on the residual, which is the residual is giving us the predicted population minus the observed population. So in our bottom-up estimate, there are certain metrics that we calculate. The first one is the bias, which is the mean of the residual. Yesterday, we calculated the bias. We have the imprecision, which shows the standard deviation of our residual. Then we have the inaccuracy, which is the mean absolute value of our residual. You can also calculate your mean square error, which is the mean value of the residual raised to the power 2. Then you can calculate your root mean square error. You can also find the correlation between your observed value and the predicted value. And then there is also another statistics. So I've shortened it. It has to do with the proportion of the predicted value that falls within your credible interval. When that value is closer to 95%, then it means you have a narrow confidence interval and more of your predicted value are falling between your credible interval. So we calculate those metrics. So we run line 214. And then we observed the metrics. Yeah. Okay, zoom. Yeah. So these are the metrics from our model estimate like we did yesterday. And it's saying that our bias is very low, which is good. And the imprecision, which is the standard deviation of the residual, it measures the variability respect to the predictions that we've made. We have our inaccuracy. We have our mean square error, our root mean square error, and our correlation. Our model is really not performing well because the correlation between the observed and the predicted value is less than 1, right? And here, the proportion of predicted value falling between our confidence bound is also very low. So our model is not doing very well. So, there are what is called overdispersion when it comes to population. So when you model population count using a Poisson distribution, you are really not going to get a good fit respect to your predicted value. So we are going to use what is called a log normal model to model our population density, and then we can multiply it by our building area. So this is just a basic model using Poisson to show you that the reason why in WorldPop we fit our model using a log normal model is that when you use a Poisson model to fit our model, it doesn't really perform well, right? And you can see we will compare these results, these metrics, with the results that we will get in the second model that we are going to fit. See? Okay. All right. If you have any question, just stop me and then I'll answer your question. Okay. All right. Go to my PowerPoint. My PowerPoint. Go back. Okay, so I think it's a time for lunch. So when we come back from lunch, then we will continue. Okay, so it's time for lunch. When we come back from our lunch, we will continue with our predictions. All right. Hello. Can you hear me? Can you hear? Can you people hear? Okay, I'll talk very sharp. So because of our time, we have to start. I don't know where the rest are, but I think when they come, they can join us so that we make progress, right? Otherwise, we have a lot to cover today. We are far behind schedule, so we have to keep going. So what we are doing is that we are building various models, and at the end of this class, we are going to assess the performance of all the models we are building. And then we will select the best one and use it for overall prediction across Nigeria. So we are building incremental models. The first model we built was the Poisson model. And one of the things about count data is the issue of overdispersion, where in Poisson model, your mean value should be equal to your variance. But that is not always the case, leading to a statistical concept called overdispersion. So the bottom-up model that WorldPop uses, we use a log normal model to fit population density. Then afterwards, we multiply the population density by the area, and then we simulate from a Poisson distribution to get the number of people within a given cluster. And one good thing about STAN is that with STAN, you are able to write a bespoke model, a customized model to define your likelihood with respect to the data that you have. So you can write your own statistical model in STAN.
Try to even louder.
Okay.
Louder, okay?
Okay. All right. So in STAN, we can write our own statistical model to make a prediction. And that's the good thing about STAN. So the next model we are going to fit, this is how we have parameterized it. We are saying that population is a function of population density multiplied by the settled area, right? So to model population, we use a Poisson model where we multiply the population density by the settled area. But what we need to do first is to model this population density and get predicted value for population density. And then the next thing is to multiply it by the area. It's just simple calculation. Then we simulate from a Poisson distribution. So we are saying that population density is log normally distributed, right? With a mean and a sigma. These are the two parameters with a log normal model. The reason why we use a log normal to model population density is to ensure that our population density is a positive value. So a log normal model, when you make prediction with a log normal, you fit a model with a log normal model, all the values that you will get is positive because population density is a positive number. You cannot have -4, 5 as a population density. It doesn't make sense. So we use a log normal to model the population density. And when we get the predicted value of the density, we multiply it by the area. And then voila, we get our total population for a given cluster. Right? Are we okay? So this is the model we are fitting. So the whole WorldPop bottom-up modeling is based on this formula that I'm showing you here. So from now, all the models that we are fitting, they are all going to be a log normal model, right? So the log normal has two parameters. It has the mu and also the sigma. The sigma is your error. The mu is your expected population density. Okay, so we go to the scripts. So, okay. So essentially, this part of the script is what I explained in the PowerPoint, right? So we are model population as a Poisson process with population density multiplied by the area. But population density, we model it as a log normal. So we do this first, and when we get this value, we come and slot it in here and multiply it by this, and then we fit this particular model. So we are creating a customized model to get human population per enumeration area. So, and we are assuming the following priors for our model. We are saying our mu is normally distributed with a mean of 5 and a standard deviation of 4, right? Usually, the first number is the mean value. The second one is the standard deviation. And we are saying our sigma, which is our error, is uniformly distributed with a mean of 0 and a standard deviation of 4, right? So those are the two priors that we are using to fit our model. So line 265 is just simulating or plotting our priors. So we will quickly run through it. When you go, you can take your time to explore what we are doing. So this is the priors that we chose. So we are plotting them for mu and also for the sigma. So start running, run 265, run 268. And then you come and run from 270 downwards. So all these things are kind of looking at our priors. What information are they building into our model? Run, yeah. Run. So run to the part where it has a fit. Okay, yeah. So everybody should run their scripts and then stop at this location, 304. Because the first part is we don't need it. It's just thinking about our priors even before we fit the model. Are we all on line 304? Okay, right. So now we are going to fit the model that I showed you in the PowerPoint. But before we do that, run line 304 up to 308. And then run your parameters. Okay. So on line 315, this is the stand model that we are going to fit. So we want to see the functional form of this stand model. So go back to your day 3 folder and go back to your script folder. Day 3 script and open. Check the name again. Open model 2.stand from your script folder. Model 2.stand. So here is it. This is the stand syntax, model 2.stand. Open it and let's see how the code have been typed. Have you all opened it? Right? So here we first define our data that we are going to use and our parameters that we need to model in the parameter block. Then this is where we specify the model we want to build. So first, our model will evaluate the population density, then it will come and evaluate the population. And come down. In Stan, there is an optional block called generated quantities, which we use in making the prediction. So when you fit the model and you want to make predict the number of people, we include it in the generated quantities block, right? This is an optional parameter if you are making a prediction, right? Are you all okay? Okay. Should I go on? Should I move on? Okay. So you can close this model 2.stand and let's run line 315 where we are predicting population. Are your models also running? Okay, mine has finished running. I didn't get any error. Has yours also finished? Okay. Error. Error. Is anybody getting an error? Okay. So our model has finished compiling. We look at whether the model is doing what it's supposed to do to see if there are any errors. So to check if our model is doing all right, you can use any of these lines, line 327 or line 328, but only run line 328. But any of them, they are basically doing the same thing. So run line 328 and let's see if we had any issues in our compilation. Okay, so when you see these things here, it means your model is doing all right. Usually, if your model fails to compile, it will throw an error here, even before you run line 328. But when you see something like this, it means our model is doing fine. Now we check the trace plot to see if our model is converging. So run line 331 and 332. So our mean is converging because you see that the chains are mixing very well. Are we okay? Now we want to look at the predicted population density for each of the observations that we have modeled. Then we will look at the predicted population of each of the observation. So first, we check the predicted population density. So run from line 336 all the way downwards. Okay, when you get to line 356, just stop. So when you, just like we compared our predicted population with our observed population in the first model, we are doing the same thing here, where we are looking at our predicted population density first with the observed population density using scatter plots, right? Then we will do the same thing with the predicted population and the observed population. So run line 356. So this is a scatter plot showing our predicted population density and our observed population density. We go on and do a histogram showing our predicted population density and our observed population density. Then we calculate a matrix to estimate the metrics that we calculated, such as the bias, the imprecision, inaccuracy, the correlation, and so forth. We will do the same thing for population density in line 392. Okay. So here, these are the metrics from the population density, right? But in our model, we say that when we get population density, we multiply it by the area to get our population. So let's see the predicted population in our model now. So the next section looks at the predicted population within our model. So run everything to the last end. So this is a scatter plot of the predicted population and the observed population. We will do the same thing for the histogram, and then we'll do a density plot. Okay, so this is the histogram. And this is a density plot, but the title is deceptive. It should be density plot, not histogram plot, right? But the histogram and density plots are the same. Okay, so this is the model metrics that we have respect to the log normal model that we fitted in addition to the Poisson model, right? So we have our population density having a bias of 8.2. And then our population estimate, actual predicted population estimate, has a bias of 61 people. And there are other metrics too. And our correlation is also very low, right? And the reason why our model, so these metrics, when you look at them alone, they don't tell any story. But when you fit different models, then you can use these metrics to compare which of the models that you fitted is actually doing very well and which one is actually doing very bad. So we are building our models incrementally. At the end of the day, all the models that we fitted, we are going to compare their results and then decide which one was the best. Are you okay? Right? So just don't worry about the model metrics now. Let's fit our model. We will compare all of them and see which one was doing very well. Great. So this is the log normal model that we've used. And this is called an intercept only model because we don't have any covariates within our model. We are just only estimating the intercepts in the absence of any covariates. So we are going on, we are building slowly so that you understand. So now you've been able to predict population within a given location, right? Okay. Okay. Can you go to the PowerPoint slide? Come down. Yeah. So the next model we are going to do is to model what's called large-scale spatial variation. Sometimes our population are grouped respect to certain clusters, right? So you may have a particular enumeration area, which is rural. You may have another enumeration area, which is an urban cluster. You may have one, which will be a dense urban cluster, right? So all these categories of settlements that we have respect to the enumeration areas can also influence our results, because we know that in rural areas, the population will be less compared to urban areas, right? Sometimes too, the admin units that a particular cluster is found in also kind of differentiates the population sizes that we will see. So I don't know which of the provinces in Panama has more population. Panama, right? And which one has small population? Roughly. Cochrane, right? So Pare, right? Okay. So those from Panama, you know, so we can see that population sizes kind of differs depending on the province or even the settlement type that particular cluster or enumeration area is located in. And so in the modeling, we account for all these variation when it comes to population sizes. And we do that using what is called a mixed effect modeling or a hierarchical structure modeling. We incorporate all these small variations in the population modeling so that they are being accounted for. In our Nigeria data set, there is a column showing the regions where each enumeration area is found, right? So when you map their mean population per region, we have 11 regions with box plots. We see variations when it comes to their population density, right? So we need to account for this variation when it comes to the distribution of population density or even population. And we are going to use what is called a mixed effect modeling. And what a mixed effect modeling does is that it assigns what is called a random effect to each of the factors or each of the clusters. So all the enumeration area belonging to region 1 will have a baseline population value. All the enumeration areas belonging to region 2 will have some kind of base population value. So that becomes a mixed effects modeling, right? In addition to having a general intercept, there is also variability depending on the region in which that enumeration area is found. So we need to account for it in the modeling. So that is the next model we are going to build. So scroll down. Yeah, next slide. Next slide. Okay, go to this one. Population density. No, the 51. Okay. So we also know that our population density or population also varies depending on the kind of settlement type that an area has. No, 51. Okay. Okay, I think you all have your slide. So open to 51. There is a bit of a delay. Okay, sure, it's here. So we know that population density or population in general varies depending on the size of settlement, the kind of settlement an area has. So we know that rural areas will have a much smaller population when you compare it to maybe towns, and when you compare it to maybe a dense or a city, a dense urban area or a city. So we see variations when it comes to the size of the type of settlement influencing our population, and we need to account for it in our modeling. right? Using a mixed effects modeling or a hierarchical modeling. So the next model in the Nigeria case, we have 6 settlement types, right? I think the first one was corresponding to rural areas. The second one was, I think, towns. No, the first one was, I think, villages. This one was kind of rural area, towns, then a semi-dense urban area, and the fifth one was dense urban area. So all these will influence the kind of population that we will see. So we go back to our script and then fit a model that accounts for variation with respect to settlement type and variation with respect to the region in which a particular enumeration area is located. Slide, PowerPoint R. Okay.
Retroso entre que le doy la orden y llega. Okay. I'm just telling you that
So it looks like the internet connection is an issue.
Yeah.
Okay.
Showing in this. Okay, it's coming. It's coming. Glow. Okay.
Okay. Okay, so this is just a plot to show you what I've just explained. So run line 509. So these are the settlement types. You see that population density kind of varies using the scatter plot. You run the next line. Okay, this is the region in which the enumeration area is found, and we see variation when it comes to population density. So the next thing is to do a mixed effect modeling, accounting for only settlement type. So this is a mixed effect modeling accounting for only settlement type. We are running. So run line 553. Then you come and run line 561. Then this model 3.stan is our parameterization of our mixed effect model that account for settlement type. When you go home, you can have a look at the way the model was written, but let us run it now. So run, okay, yeah. Run line 566. So it takes a while for mixed effects or random effect models to compile. So depending on the kind of machine you are using, your model can compile very quickly. If your machine is old like mine, then it would take time to compile, right? So we will get there. Whose machine has finished compiling? Okay, so those people are using very powerful machines. No, I think 3. 1, the back, and 3, yeah. Okay, 4. Okay, yeah, so my machine is also powerful. It has just finished compiling. So we just do basically the same thing, check our diagnostics to see if our model is doing well, do our metrics to assess model performance. So, I mean, I've explained more on some of these things. So just run line 577. We do our trace plots. No, wait. It's fine. No, don't stop it. Okay. It's fine. That's fine. Okay, yeah. So our sigma is converging. And I told you about the settlements. Yes. So this is the intercept. The parameter intercept, which is alpha, it has converged nicely. Yeah. The next one is the providing an estimate for the different settlement types that we have in our data set. So all the enumeration areas or observations that belong to settlement type 1 will have this particular estimate or 1 alpha value. If you belong to 2, you have this alpha value, right? So we are accounting for variability when it comes to our settlement type in modeling our population. And that is a random effect model, right? So we have 5 settlement types, and it has estimated the parameters, random effect for all of them. Okay, just move on. I just wanted to show that. So run through the model to the base. Yeah, run the estimates, run the population density. Yeah, run. So this is the scatter plot of population density. So we are essentially repeating the same thing, right? With respect to different models. Run. Run again. Run. Run. Go ahead, run. 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 Run again. This is the predicted population versus observed population. Yep, go ahead. Go ahead. Run again. Run again. Yes, run. Open this one wide. Open it wide. Zoom. Can you pull it down a bit? You can. Okay, so by incorporating a random effect for settlement type, our model is slowly improving over the previous models that we fitted. And you can quickly see that with the correlation between the observed and the predicted value. So the previous models that we fitted, the correlation is less than 10%. But when we accounted for variation in our settlement type, we are seeing that our population, the correlation between the predicted population and the observed population is somewhere around 30%. So our model is slowly improving, right? So we started from a baseline model, and then we are fitting different models to see how they are performing. We are going to compare the results soon, so just hang on. So the next model we are fitting is that we are going to account for variation in settlement type and also variation in regions. So the region could be variation in provinces. If your country has province as one of the administrative units, you can account for it in the modeling. So that's the next model we are building. So we are predicting population, human population, respect to these models that we are building. Okay, calm down. Go up a bit. Okay, so like I was saying, the next model account for random effect by settlement type and by the region in the modeling. So run to the last part of this model. Run everything. Just run line by line. Okay, let's wait. Whose machine has finished? Okay. They always finish first. They have really good machines. Okay, so our model has finally finished running. Let's look at our trace plots for the parameters. We look at alpha, which is the intercept. It has converged very well. We look at our settlement intercept. It has also converged very well. We look at our regions. Open the regions, zoom in. So we have 11 regions in Nigeria. And so our model is estimating an intercept for each of these regions, right? So we have accounted for regions in our modeling. This region can be a province in your home country. Close it, yeah, close it. So run the rest, let's run to the last part of this particular model, and let's look at the metrics. That's the model estimate. Yeah, run, yeah. Yep. Yeah, okay. Okay, so when we accounted for a random effect for the settlement type and random effects for the regions, our model is still improving compared to the previous models, right? When we compare them finally, you'll be able to see how the models are performing. But in our previous model, where we accounted for variation in our settlement or random effects for the settlement types, I think the correlation for that model was around 30%. And now we are having 0.44, which is 44% between the predicted population and the observed population. So we are still improving our model. So the next one is to do another mixed effect model, or called a hierarchical model, where we account for variation when it comes to the region, and then we look at different combinations of the settlement and the region. right? It's called a hierarchical model. So first we look at overall variation at the regional level, and then we look at different, you can say it is an interaction model, different combination between settlement type and the region to see how the model is performing, right? So that is the next model that we are going to do. And yeah, run this one. Run. Run, yep. Run. Okay. Can I see all of the statements? Note on initialization. Okay. Shift it. Okay, that's fine. So this model is actually going to fail, right? And I'll show you the reason why this model is failing. So I brought this model to show you some of the things that can go wrong when we are doing a random effect model. So this model is not going to compile, it's going to fail. But just to show you what was wrong so that you understand anytime there is an error, how do you debug an error in your Stan script? If this model compiles for you, then it means your machine is super excellent. I know it's going to fail, right? Because I've tried it several times. Okay, so you can see the first statement has shown Stan model does not contain samples. So it's failing, but we just need it to finish. But when you see this statement, it means there's something wrong with the model. Yeah, yeah. That is the reason why this one is failing. So I'll explain that. Okay. So the reason why this model is failing is because in the other models, you will see an argument called INIT equals 0. But in this model, we see that we don't have that there, right? This is what is happening. When your Stan is sampling, if you don't supply, it's called initialization, that's INIT equals 0 in there, it starts sampling respect to values in between -2 and 2. And sometimes it overshoots your Poisson rate. So it gives, there is a maximum value that you can get for Poisson rate. So if you don't constrain your model very well, your model will be overshooting beyond that Poisson rate, which is statistically impossible. And so the model would go ahead and crash. So now we need to do a model where we specify, come down in model 5, where we specify this particular argument, right? So that the model is constrained very well and our pursuit rate doesn't overshoot, causing our simulation or sampling to crash. Are we all clear? See? All right. So we run stand model 5, and there's also going to be another error that I need to explain. So hierarchical models are notorious for some of these issues when you are fitting a more complex, because it's a more complex parameterization that we are doing. So some of these issues tends to crop up, and you have to know the way you can diagnose or bring a solution so that the model will run. So this particular model will run, but we will see some warnings that we don't have to neglect. We need to fix those warnings, but this one will run okay. Okay.
You can see like
Okay. How many of you are seeing the warnings? I think you have the warnings. Mine is still running, so I have to wait. You have warning? Is it warnings or error? Warnings. Okay. Wow, my machine is so slow. Natalia, can you make this, shift it this way? Yeah. Oh, so so my machine has crashed. I have to start all over again. So it's not powerful enough. So can I use someone's warning to explain, if you don't mind? Because if I want to start all over again, I'm sure it can probably crash again, right? So can you log into Zoom? So you stop sharing mine, log into Zoom then. Yeah, so in making population prediction, in our last day, we are going to create a raster of populated pixels. And these are some of the things that can happen. We deal with huge data sets, right? And even with a small data that we are going to test tomorrow, I'm sure, I don't know if mine will be able to run, but we handle very big data sets. And so you need very good machine. So my machine at the office runs very well because it's very high spec. But this one, I don't know what happened. And now it has crashed. So maybe you should stop sharing so that she share. Has anyone's machine also crashed? No? So it's only me. Okay. Yes, so when you run that model, you see it's saying that we have 283 divergent transition and the tail effective sample size is too low. This is what is happening. Anytime you run scan and you get this warning, divergent transition, don't ignore it. This is what is happening. Your scan model is kind of sampling, right, around the posterior. And sometimes it takes large jumps because of the parameterization, especially it happens with hierarchical models. So when it takes large jumps, it results in what is called divergent transitions. So for example, if you are descending a very steep hill, right, and you don't walk slowly, but you decide to run, you fall off the cliff, right? So that is what is happening. So we need to make sure our stand model is taking smaller steps so that it doesn't result in the sampling shooting off in the model. So that is divergent transition. And when you get divergent transition, it means that your predicted estimates are unreliable. We cannot rely on the predicted estimate. So make sure you fix the divergent transitions before we move on. And there are different ways of, calm down. Oh, I think up, yeah. Okay, yeah. So there are different ways of fixing the divergent transition. There is a parameter in STAN called adept delta. Adept delta. When you put that parameter there, and then you specify 1 or 0.99, Stan is going to be taking very slower steps, which will slow your machine down drastically. So instead of running or simulating very fast, it will slow it down so that it can sample your posteriors very well. There are other things that you can also do. You can decrease the step size, or you can reparameterize your model using what is called a non-centered parameterization. So I won't go into details with respect to that, but in your scripts, if you look at your Stan files, I have some of them where I have done non-centered parameterization to avoid some of these divergent transition. So yes, so that is what we are doing. We are running another model again to fix the divergent transition. So run that particular model. Can you run at the paragraph and let's see? Up to one, up to this. Yeah, just run everything. So we've used what is called a centered parameterization, where the variance parameter is, I don't know, can you open? So many things have changed. No. Yeah. Try the PowerPoint slide if you can share, or if you can share your PowerPoint, let me explain what is happening. Day 3 PowerPoint.
Where in the installation, predicting
Come down.
Oh,
Yeah,
down.
down. No, up. Up. Yeah. This one, let me. Okay. So sometimes the divergent transition that you see is as a result of the way we parameterize our random effect components. So we have a centered parameterization and non-centered parameterization. Assuming tau here is the variance parameter for our, let's say, settlement, right? Then in terms of estimating the random effect, we bring the variance parameter tau k directly into the modeling. So in estimating theta, which is the maybe random effect for settlement, this variance parameter is brought directly into the parameterization over here. And this is called a centered parameterization. This can result in divergent transition. So to solve it, we have our variance parameter here defined by our mu, which is the mean and the sigma. Then we specify another form of parameter, which also has a mu and a sigma of 1. So that when we multiply them rather than incorporating them directly like we have done here. So this is a non-centered parameterization, right? So sometimes when you do this, it can result in divergent transition. Sometimes when you do this, it can also result in divergent transition. So you need to check which one is working best, especially when you are dealing with a mixed effect model. So the model we are implementing now is writing the model again using this particular centered parameterization, right? It's a bit more of going details into statistics, but this is what we are trying to do to avoid the divergent transition that we are seeing. I hope that is clear. So let's see if okay, so still, even after we use centered parameterization, we still have divergences, right? Sometimes the reason for the divergences could be the fact that we don't have a very strong prior. So the next model we are going to fit, we are going to make sure our random effect components in our model have a very strong priors to reduce these divergences. So we still have warnings and we need to fix them. If you see warning, don't try to avoid it and run your model or go ahead. If you have a warning and you don't fix it, your estimate will be unreliable, right? So we need to fix this warning that we are still seeing. So calm down. Okay. We are going to run. So with this model, I use some strong priors on my random effect component to avoid the divergent transition. Okay, so you see the warning. Okay, yeah, that's fine. I hope we are all clear with what's happening. So if you are making prediction with your population data for your home country, you will see some of these things and you must know how to fix them or how to go about them. This one will still have a small number of the chains, small number of the sampling having divergent transition, around 7, but I read on it and it looks like they are false positive, right? So we are okay to go. There is a literature which suggests that if your divergent transition is somehow below 10, you are okay to go. I think I need to find that paper again and then share it on the page. So those are false positives. So we can just ignore it and go ahead because the divergent transitions are very small. And divergent transition are very common with mixed effect models or hierarchical models. Okay, so if your machine crashes, you start all over again. Here has crashed. So if your machine crashes, you start all over again from the beginning. So where are you? Okay, okay. It's okay. Okay, sure, let's see. Let's see how it is. Samela. Samela, right? Samela. Elena, sorry. Okay, so it looks like your model ran fine, but there's still a warning here. So let's check the model diagnostics and see. Okay, yeah. So when we ran our model diagnostics, I was thinking there will still be some divergences, but I was wrong. There is there's no divergent transition with our model. So I don't know why this warning is coming, but it has nothing to do with our model. So our model is now very fine and we can proceed. Our R hats. So when you run a stand model, there is another statistics that it gives called R hat. Your R hat should be closer to 1, right? When it is above 1.05, your estimates are unreliable and you need to fix what is happening. But we don't have any problem. So we can now continue, move on to do our histogram and then calculate those statistics. Yes, so do the first trace plot, which is the intercept. Do the second one, which is We don't, yeah, you can close it. Do this one. So okay, zoom in. Yeah, make it very big. I want to explain something here, then we'll move on. This one. It's freezing. Okay. Okay. So this is a hierarchical model. And in our data set, we have 11 regions and 5 settlements, right? So what you are seeing is that it is doing an interaction between the different regions and the settlement type. So multiply 5 by 11, what do you get? Around. So it's kind of doing different combinations. So if we have settlement 1 in region 1, settlement 2 in region 1, settlement 3 in region 1, settlement 4, and then you move to settlement 2 in region 1. So it's doing different combination to estimate different random effects for our model. And this is what is called a hierarchical mixed effects model, right? So what you are seeing there is the different intercept that it estimates for each of the various combinations. So you can close it. You can skip the scatter plots. Let's move quickly to the base. Run to the base. Yeah, the estimate. Yeah, run every line from here. Go. 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 Oh. Can you run it line by line so that I move? Stopping at, I have some comments at the base of this model. So just you come down. Let me show you where you have to stop. Come down. Come down. Okay, you stop here. So starts running from the, yeah. No, you have to go up. 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 Start from the up, yeah, up. Yeah. So come down a bit. So run from here to the comment I showed you. You can run it line by line, or you can. She wants to run the whole thing, so. Okay, yeah, that's fine. Okay, you finish running it. Let's see the statistics from our model. Make it, okay, make it big. Okay, so when we did a hierarchical model, we've seen that our model has further improved, right? First, our correlation was around 44. Now we are having like 50% correlation for predator population. And then the population density correlation is around 67%. So now we've completed with our models. The next line is to compare all the models that we fitted, compare which one was doing very well, and then we can do further model checks. I think model 1 is the first model. I think that's the Poisson model. Yeah. No, so no. You have to run the whole model 1 script, because the model is doing that, so it overrides the previous posteriors. So you have to run from the beginning of model 1. Okay, yeah. So just run from here. Yeah. Okay. Have you been able to see the comparison of the various models? Come down. Come down. Come down. Okay, start from here and run to the end. Okay, yeah. Okay, let's compare. Okay, so make it big. Okay, so this is the population estimate with respect to the various models that we fitted, right? The first model we fitted was a Poisson model, and it has a bias of 35, right? The smaller the bias, the good the model. The imprecision is also very low. The inaccuracy is also low. Mean square error is low. So all these values must be low. All these statistics, if they are lower, is good. Then the correlation, there's something wrong here. The correlation that we had with the Poisson model was less than 10%. If you people do remember. So your Poisson model, your model 1 there's something wrong. Are you getting this? Are you people getting the same results here? Here? No? It's smaller. Yeah, so maybe we jumped something in your listing. Yeah. So the Poisson model was West, is the West model, right? Yeah. And when we compare our second model, the log normal, we are seeing so among all these model, yes, so the first Poisson model and the last one, the values are the same. So you have to run the first model again, and so that's the reason. But Poisson model was the worst if you compare all the models. And the best model is the model with a hierarchical effect for settlement nested within regions. Because when you compare it, its bias is very small. Its imprecision is also very small. Inaccuracy is very small. When you compare the mean square error, is better than the other models. The root mean square is also better than the other models. And our correlation is also higher than the other models. And we have 95% of the 95% of the predictions falling within our lower and upper credible intervals, right? So we've predicted population using various models. You can also look at the metrics for density and you do the same thing.
Gracias. ¿Este sesgo está en porcentaje? Y disculpe, no vi cuál es la definición de ese sesgo. ¿El sesgo es un sesgo relativo en porcentaje? Si es así, 35% no es mucho.
So the bias is not in percentage, it's just
Okay.
mean of the residuals.
Okay,
Yeah,
okay.
yeah. So it's not in
Gracias.
percentage. Okay, cool. Okay, so now, are we all okay? Do we need a break? No. Today we are far behind time, so can we quickly jump on, right? So you can see that we haven't actually introduced covariates or independent variables in our modeling. Most of the variables that we've introduced are random effects. It estimates random effect. So we need to incorporate covariates that will explain population within a given area. And that will even improve our model even the more. It will make it more powerful. So that is the next step we are going to do, to incorporate independent variables that explain population density in our model. So you can close this. The density we can just forget. So we are going to go to your day 3 and then open workflow 3. Day 3, workflow 3. So I think I can share. So if you can stop sharing. If you want to stretch a bit or take some coffee before we start the next one, I mean, you are free to do so, right? I hope you people understand what we are doing. So it looks like you are just running lines of code. But when you sit down and you kind of read more on them, you would really understand what we are doing, right? Yeah, workflow 3. Yeah, just open it and change my, yeah, copy this part, copy the part from 2 and change it for me. Okay, can we call the remaining people to come in because we have less than 40 minutes to finish the next models. So we have to hurry up unless you people want to give me extra 30 minutes of your time. Okay, so we are starting. All right, so the previous models that we've done so far, we have not accounted for the effect of geospatial covariate in our modeling. We know there are certain factors that still affects or is associated with population density, right? Such as distance to road, for example. And so the next model that we are coming to do is accounting for other geospatial covariates that are associated with population or that can be used to predict the population within an area. And some of these things can be like distance to roads because people tend to live closer to the roads, especially for Panama. When we went to Portobello, most of the settlement is along the road. You can have something, a covariate like slope. People tend to live at low-lying location. Only relatively few people live at higher altitude. So slope can be a factor that can affect population distribution. So we need to account for some of these covariates as part of our modeling. So this is what we are doing next. So click this one. Okay. Oh, it's not showing. So there are a large number of geospatial covariates that you can use as part of the modeling, but you have to select the best ones that kind of help predict population density or population. Yesterday, we did a few examples where we extracted some covariates. Then we did a stepwise regression and to see which one will be able to predict population density. I hope you guys do remember yesterday in the morning, right? So in predicting population, we have a large set of covariates, but we need to select a few of them that has a very good effect or powerful effect on population distribution. So in this model that we have 6 geospatial covariates which were selected that predicted population density in Nigeria. Go to the next slide. Yeah. No, the next slide. Okay, so these are the covariates that were used in predicting population in the Nigeria modeling. One of them is graded population estimate. So previous population models that WorldPop did, we used that one as one of the covariates. We have school densities within a 1 kilometer radius, kind of doing some zonal statistics in GIS, Geographic Information System. We have household sizes. We had household sizes from DHS, which is the Demographic Health Survey results for 2013. We had their household sizes, and then we interpolated it to create a surface, because we know household sizes also has an effect on population. We have the settled area within 1 kilometer buffer radius. We have residential, non-residential areas. So these 6 covariates in the Nigeria model that we did were able to have, they had a strong effect in predicting population density. So we are just going to use the same covariate to see their effects on population in our model. So open your scripts. Open day 3, go to scripts, and open workflow 3. Okay. If you are there, make sure you correct your path. If your path needs to be changed, make sure you do that. Right, I have changed mine here. And then there's a brush, there's a symbol here. Click on that symbol to clear anything from your memory when you open your workflow 3. There's also another brush here. Click on it to clear anything from your memory. And then you do the same thing for your environment, so that we start at fresh. We have a fresh memory to work with. Are we okay? So start running your libraries. Run. If you don't have our color brewer, I don't think we need it here. So you can just forget about it, or you can go ahead and install it. But we wouldn't need it in here in the workflow over here. But you can just install our color brewer quickly if you want to. Okay, are we okay? So you read in your path. Yeah, go ahead. You read in your stance setup. You load, we are using the same data set, so you load your data. So read, run. It's okay. So now, our covariates, we've named them X1 to X6. So we are going to see the relationship between our covariate and population density using a scatter plot like we did yesterday. So line 43 is going to do that for us. Okay, so now we have a scatter plot between our observed population density and the covariate, right? So in general, so this one is a linear relationship. So the first covariate, which is previous WorldPop estimate, it shows a linear relationship between population density. This one is distance to school, x2. So there's a linear relationship between the distance to school and our population density, right? And so forth. So we can close it. Okay. Now, our covariates are on different scales. So yesterday I explained what is called z-score, right? Which we use to scale our covariate. So we are going to scale our covariate using z-score, where we find the mean of each of the variables and then subtract it from each observation and divide it by their standard deviation. So we are going to scale our covariate using z-scores so that they can be on the same scale. So run line 52. And then we get for each variable, we get its mean and we get its standard deviation. So line 56 is doing that. So run line 61. Okay. So with the scripts that we run, for each covariate, we have these are the covariates, their mean, and their standard deviation. We will store this thing as an Excel file because when we are doing prediction at omitted locations where we didn't gather data, we will use this particular statistics to scale our covariate during prediction. So we need to store this somewhere, right? So this line here will create a CSV path that stores your mean and your standard deviation because we are going to use it tomorrow in making actual population prediction across the entire country. Okay, so the next thing is that we use this function to actually scale our covariate. So using z-score. So this function actually is using z-score to scale our covariates. Run this one first before. Then we apply, there's a function in R called apply. If you want to apply a function or you want, such as mean to every column in your data set, you use what is called an apply, and we have different varieties of the apply function. We have lapply, which works with lists and so forth. So that is what we are doing on line 76. So we then join the scaled covariate to the actual data using column bind. And so let's look at our data set again. Click on the environment. Go to environment. Yeah, pop data is down. Yeah. Open it. Okay. So now we can see that our covariates have been scaled using z-scores. That's why some of the values are negative, others are positive. So we are ready to run our first model by accounting for the effect of these covariates on population density. And we are basically following the same steps like workflow 2. So we'll run through this one quickly, right? Because of our time. Yeah, run. So run your first model. So this model is only the covariates or the independent variables. It's looking at the effects of the independent variables on population density or predicting population density using the independent variables, also known as covariates, also known as predictors. Has your models finished running? Yours has finished. Okay. I think my laptop is tired, so it's now running very slow. Have your models finished? All right. So continue, check, run your trace plots, continue to the last end of model 1. Okay.
No sé, yo lo corro aquí, pero ya se copió. Total. Yo decía, pero no lo hice. mire lo que dice. No, no, es que dice una opción para que le ocurra a todos al año.
Okay, my model has finished. So we check model diagnostics to see if it's doing very fine. And then we will check the trace plots quickly. Then if you just continue running your script to the last part of model 1. Wait, when you get to, okay. Yes, so these are the estimate, the trace plot for the covariates, the beta parameters, right? We have 6 covariates. So the model has accounted for them in our model. And this is the trace plots here. So we go down. Yep. Yeah, carry on. Carry on. Yeah, carry on. Carry on. Carry on. Carry on. 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 Carry on. Carry on. Okay, yeah, we stop. Yeah. Okay, open. Okay, so the first model we fitted is only accounting for the effect of the geospatial covariate. And we see that it's not doing so good. So the correlation between the observed and the predicted is around like 24%. So we will fit another model where we account for a random effect for the settlement and a random effect for the regions in addition to the covariates, right? We will do a second model. So just as we compare the first one, after this one, we will compare everything. So this one, we are doing a random effect for settlement, a random effect for the regions, in addition to the covariates, right? So previously we didn't, in the workflow 2, we accounted for random effect for settlement and random effect for the regions. But now we are adding our covariates as part of the factors that explains population density in Nigeria. So we run this model quickly. Yeah, carry on. Has anyone finished their model? Has their model completed the sampling? Are you done? Okay. Yeah, it will take a while to complete this model. So there are a lot of resources on Stan online, and as well as Bayesian regression. So if you want to read more on that, you can just go online and look at those materials and then read more on Bayesian regression and even how to use Stan for Bayesian regression. There is also another package called INLA, which is more straightforward. You can also have a look at INLA if you want to do Bayesian regression, right? Yeah, you can only use this thing to refresh. So it's sampling. Oh, okay, yeah, sure. Go to the scripts. Click here, let me see which Stan model you are compiling. Yeah. Slide this one here. So model 2 beta, go to the script. Model 2 beta dot stan. Okay. So this is how the Stan script look like. I mean, we have, oh, okay. Okay, but can you shift this one here? Or you can shift it unless you start.
No, I'm gonna start again.
Start. Okay, so my machine is not strong enough. Can you use your machine again? Isabella, can we use your machine again? Or you're doing something? But okay, that's fine. I think it will crash again if you run it again. Can we use your machine? Okay. Oh, okay. Yeah, but you can show him the model 2. Yes. Do you want to see the actual model? Yeah, come down. Yes, so I mean, which one do you want to see the model? Come down. Yep, this is the model. So this, yeah, No, they are individual random effect settlements. They are not nested. The nested one is the nest model. Mhm. Yeah, sure. So that is the model we are fitting. No, we are doing model 3, workflow 3. If open, so close this one. Close workflow 2. And then you can start running from the beginning. Can you stop sharing so that you have to stop sharing, right? It's stacked. Yours is stacked.
We're now installing the applications.
Okay.
Dos model 3 están model 2 del model 3. Eso fue el que para la
Yeah, so it's almost 4:30. Can I borrow 30 minutes of your time? Yes? Are you deciding for them? So can I borrow 30 minutes of your time if you don't mind? Right? So that yeah. So today is like a bad day.
Se voltea. Hay que decirle compartir pantalla.
Y ahora sí. Bueno, siléncialo también.
Okay. So yours has finished. Run the model checks. Okay, so this is our alpha parameter. No, don't zoom in, just run. Run. So this is our scatter plot. This is our density plot for population density. Okay, yeah. Wait. Open this, zoom in. Yeah. Click on the zoom. Okay. So this is our model metrics. We've seen that our model has improved again when we accounted for the random effect for settlement type, for region, and then for the covariates compared to the previous model. So close it. Come down. Yep, run. So the next model is a hierarchical or nested effect model where we have settlements nested within regions like we did previously. And at the same time, we are accounting for the effect of the geospatial covariates in our model to predict population density. It's okay. Let me see something. I'm watching something the last. Okay, this was just to compare the three models and do cross validation. And then we are done. So we just finished. So okay, so with this model, we have like 10 divergent transition, which is okay to go when the divergent transition is a lot, then you have to fix it. But this one is 10 is probably some false positive in the model. So that is okay to go. Run this line. This one here. Okay. So this is our alpha. Run. These are our beta trace plots. They are doing very well. They are mixing very well. Don't run this one. It will take time. It's doing different combinations. So just run this one. Yeah. Okay, so yep, go ahead, run everything. Yep. Wait, run them line by line to avoid any mistake. Okay, so start from here. Yeah, run. Yeah, run. Run up to the last part. Yep, so I think we have, so open this one, let's look at the statistics in terms of the model prediction estimates. Okay, now, so our model has further improved. The predicted population density has a correlation of around 67%, and the actual population has a correlation of around 50%, right? And the other model metrics to the values there are low. So now we have fitted 3 models, and we are going to compare the 3 models that we have fitted so far to see which one is the best. So the first model we fitted only accounted for the geospatial covariate. The second one that we fitted, we accounted for the geospatial covariate in addition to random effects for the settlement types and random effects for the regions. And this last one is called a nested effect, where settlement, we account for the covariates in addition to settlements being nested within regions, right? So we have 3 models. We are going to compare them to see which one is predicting our population very well based on the model metrics or the statistics. So the next line is to compare the 3 models. Right, wait, so let's look at the first, run this line again. And run this one. Okay. Open this one so that we can see our population density estimate. All right, so based on the predictions that we've made, the last model, which accounted for, which is a nested effect, that accounted for the covariates, and we have settlements nested in regions, was the best. And the reason why it was best is because, well, when you look at the bias estimates, the second one is better than the last one, but that is not the only metrics we are looking at. When you look at the imprecision in the third one, the nested effect model is lower compared to the second one and compared to the first one. When you look at the inaccuracy, the estimate there is also lower compared to the second one and compared to the first one. When you look at the mean square error, the value is also very low when you compare it to the other ones. So judging from the metrics, right, we can say that our model 3 is the best model when we compare it to other model. The correlation is even far better. We can also check our population density metric. So, yeah. Okay, so open this. So you can see that our last model in terms of estimating or predicting population density, the last model is still the best. About 67% correlation. It even has a smaller bias compared to the rest of the model. The imprecision is also very low. Inaccuracy is low. Mean square error is low. Root mean square error is also low. So our last model is the best model so far. So the next thing we have to do after you have fitted a model and you have a model, you have trained a model and you have a model which is doing very well, the next thing that we need to do is to see that to do cross-validation. So we are going to partition our data into a trained data and a test data. We will fit our model on the trained data using the last model, the way we parameterize it. Then we will make prediction on the test data and then check whether our model is still giving good results or it's still overfitting. Right? So after you've fitted all the models and you've settled on the best one, then you come and do cross-validation. You partition your data sets into a train and a test data. The train is used to fit the model, and then we make prediction on the test data set. Then we compare model metrics to see if it is still doing or performing very well. If it's not performing, if the test prediction is not performing very well, then it has to do with the fact that our model is overfitting our data. But if it's doing very well, then we are okay to go. See? Okay, so let's run the last one, then I think we can close for the day. So we have gone through population. So this is what we do at WorldPop. We have estimated population for Nigeria. So congratulations. All right, so let's finish with the last aspect. So the last aspect is to partition our data into train and test data. So the cross-validation we are doing is based on the model 3. The model 3, which was the best model. That is what we are using to validate our model. Okay, run. 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 Hang on. Okay, continue. Yep. So when we did a leave one out cross validation on the test data set, it's saying that the correlation has dropped to 0.4. And when you have population density is around 0.6. So let's compare it with the other models and see the results. Okay, it's okay, wait. Open this big. Okay, so our model 4, which is looking at a leave one out cross validation, is actually not doing okay, right? So it is showing that the model is underperforming when we compare it to model 3, which was our best model, which means we are probably overfitting our data set. So you go back and check and use a much simpler model, right? It could be the model 2. We can also do cross-validation for model 2 to see if you are getting overfitting or the model is performing better. Or you can go back to model 1 and you do cross-validation on it. So when we use the model 3 to do cross-validation, our model 4, which is the cross-validated model, is not doing okay. So we have to go back again and then do a much simpler model, right? So that is all about population prediction. So it takes a long time to actually get predicted population value for a given place or a country, right? Because we have to check if everything is all right before we proceed. So this brings us to the end of our population prediction. Any questions? I know it's a lot today, right? I'm probably sure you don't know where to start or where to end, but it takes time to learn a new skill. So as you have done this one, read more on statistics and then try and run all of these models on your own. So thank you very much. And if there's no question, then we'll close for the day. All right. I have to go and install some packages.
You know what? When I tried to
Is it-
reinstall them, it was already installed. Look, when I put the libraries.
Okay, then you can use your open folder 4, and let's see if it will work. If it works, I don't have to install them, then you will use your machine.
Okay.
Provided it doesn't crash.